basically do Gaussian elimination in the computer. And essentially we did first half of it. Today I'm hoping we will finish it and actually then do something with it. Okay. So, alright, so one thing that what I want to just review is what we did last time. So basically the first step in figuring out any computational algorithm is, okay, let's see how do we solve it by hand. And then in solving by hand, can we figure out how to generalize? Okay. Computer doesn't respond to you typing in a sentence, replace row 2 by row 3 times 7 minus row 5. Okay. You actually have to refer to that row, how is it stored on a computer, and then give a clear instruction. The second problem we have is that we conceptualize, computers don't. Okay? So we are actually intelligent creatures that can actually recognize a pattern, and then regardless, the moment we know how the rules work, okay, a 3 by 3 matrix comes our way, we know what to do. A 4 by 4 matrix comes our way, we will figure out what to do. And this step from 3 to 4 is knowing how concept works. Now, computer does conceptualize as long as we can refer to things, but we have to refer to things clearly, and whatever we write for the computer has to work both for 3 and 4 and 5 and whatever size we write. So in that sense, what we did last time is we actually tried to generalize our rules. So when we actually have numbers, so when I have numbers sitting here like 1, 2, 3, 4, 5, 6, okay? In order to get rid of this 4 in position A21, I know that I have to multiply first row by 4 and then subtract from the second row, okay? But if I'm generalizing the rule, I want to define what the coefficient is, no matter what the matrix is that I'm dealing with. So basically we know that I have a coefficient times A11 minus A21 should be 0, and that gives me coefficient as A20 as A11, and that's the coefficient I multiply my first row with, and then I'm subtracting the second row from it. I will do similar procedure for row 3, in row 4, in row 5, and so on, however many rows I have. So I already know that I can actually write a loop that will do that for me and basically get rid of all of the coefficients below. And that's what we did initially for the first row, but then for any. So if I imagine in this outer loop, if this is actually 1, okay, then this inner loop is what actually gets rid of the coefficients, because I start from 2 to however many I have, and I essentially figure out what the coefficient is. When j is 1, I have, and I is 2, I will have A21 divided by A11, okay? And then this is what replaces this entire row. Now this is assuming availability of vectorization, because I'm actually operating on entire row. This is the nicety in MATLAB. Some of you might have solved that differently. Possibility, this is another option, is operating on element by element. So I'm going to actually have another, and I'm going to comment it, but I'm just going to type it in so you have that option. For k is equal to 1 through n, okay? A of ik is equal to, so basically I'm doing the same operation but for every element separately. So this is without vectorization. Okay? So this operation here operates on all. And another thing is actually I don't necessarily need to go from 1, I can just go from j, but that's a minor comment here right now. Okay. So, but this, and we augmented the matrix before, so I'm done with both sides, the right-hand side and the left-hand side of my AX is equal to B. Great. Okay. So now that we're done with it, and basically always double check, so this inner loop will execute for every j. So basically I will then repeat with, since I'm replacing things within my A, okay, I didn't create a new one, then these coefficients will be updated, and now I'm working with the updated coefficients, just like we did when we were doing things by hand. And now I would start from A22 and get rid of A32, so now my coefficient would be A32 over A22, and that's basically what executes here. When my j is equal to 2, this coefficient will be 3,2 over 2,2, and I will do the same. Yes?
Would you have to have the coefficient as a separate variable?
No. This is for readability. Okay? So MATLAB will be just fine either way. The question is, will you, when you're looking for typos? So to me, it's personally easier to do that. Especially if you're actually using coefficient multiple times, you do want to store it separately. Because if you're correcting it, you correct it once and not 3 times. So that's just a practicality. Great question. All right. So now I actually tested that my A was working. So this is my test case. So my A is this, and my B is this. Yep. Okay, once again. Okay, and I can actually go and do this. And in the process, this is what A is displayed as. So I'm actually working just fine. Now I'm in this upper triangular form. Okay, and I need to start solving. Why is this x sitting there when I execute this? Why do I get x as a response? Truth is, I actually have something below here, and that something is setting x. Okay? It's just that we haven't worked this out, so whatever x is set as is not correct. Okay? So we're now actually going to work on it. But I'm printing A because that's what my function is. I typed in A here to print it out to check on it. And there's x that is started first as zeros. And I now know if I'm actually solving an augmented system that looks like this, okay? I know that I'm going to start from the back, right? So this is now backward substitution. So my last x of n, in this case x of 3, x3, will be this number divided by this number. So actually what I wrote here is not correct because this was not working with the augmented matrix. If I'm working with augmented matrix, this is actually this. And this is again because I had an augmented matrix. If you didn't work with augmented matrix, then you would have B. But then you would have to also change B here, just like you changed a row of A, okay? But we didn't do that, so I'm just going to leave it. Okay? So I have the last element. Now in case of a 3 by 3 system, all I know is that my x of 3 is B of 3 divided by A of 3. And in this case, actually, I'm going to type in, since we had the augmented matrix, it's really A of 3, 4 divided by
A of 3, 3. Okay.
So you can go both ways depending whether you augmented the matrix or just worked with A and B. So this would be my, and that's basically what I wrote right here. How do I get to ones below? This is where you actually take a piece of paper and try to generalize, okay, if I have a 3 by 3 system in upper triangular form with some, you can just call these A's, how do I generalize that rule to actually then have a loop? Because I have to loop from n minus 1 all the way up to 1 and figure out what my x's are. Let's do that. Okay. So I expect you, and here there's a hint, so you can look at this hint here. And again, I'm using B's, but you would actually have to use the last row, last column of A instead. So you write this down first for x1, x2 in a 3 by 3 system, but you want to generalize it to n by n. Right? So we have to figure out what are the limits of loop and how will I actually do this for a system of any size. And this is where you need to be the person doing it. These computers cannot conceptualize. You have to tell them precisely what to do. Bless you. Alright, so Ningu and I will walk around and help out. You can discuss, work on your own, work with somebody, however you prefer to think. Because you are working on this here. There's a column, this is a row. Little typos, aren't they fun? You're like, no. That is, you have to change your definition of that. So dimensions, when it says dimensions must agree, then whatever you're adding is not the same size. You can just also go in and kind of print it out just before, and then you'll figure out, oh, there's a column here, we know just print as a just type it in and have something printed for you, and that'll help you figure out, oh, the type. I mean, I identified it immediately, but if I didn't, there could be one group of 3, that's it.
Okay. Hey, Julian. A group of 3.
Because I think we have 25 students. You have to rewrite this to work for any size of matrix. N minus 1. So nth you already have, but sure, yes, from n to 1. So nth one I already typed in. You have a lot. You have one. Yes. 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 So I'm going to do that. So we need to work from element n minus 1 down to 1.
So basically,
at least this you know, and that could actually score you a point or 2 when you're solving a test, even if you don't put anything in the loop. Knowing that you need a loop. So I ultimately have to figure out what is x of I, right?
or I have to find a pattern here that I can write.
And when you're actually thinking through, this is actually a helpful thing to write down. You kind of give yourself a visual where you need to be. And if you can't generalize from this, write what it would be in a 4x4 upper triangular system and see whether you kind of see from there. So kind of switch it up a little. Major allergies going on.
Yeah, seriously.
That cedar again? Is it always cedar? Hold on, some sort. Everything is blossom.
All the above.
Yeah, I have some blossom, but I don't know what it is. Like, but it's not jasmine, but it looks like jasmine. I know it's not jasmine. No, make myrtles a little later. But there's many. Yeah, that is. Yeah. I have 3 great myrtles, but they're not. Uh-huh. So you have to have a little loop in there creating that sum. So yes, the point here is that this sum here this thing is changing based on how many you already have computed. So at this stage I only know x sub 3 and I have to plug it in. But at this stage I already know x sub 2 and x sub 3, so I need to plug it in. So this sum here, if I had more, this would keep growing based on how many of x's you have already found. Yeah, it has to work for any n. So it has to work for a 4x4 or 5x5 or 6x6, whatever n is.
But X will only have 3, right?
No, x will have n, whatever n is. N is the
So then how do you know where one is back row?
So you know at this stage you have computed xn and all of the other x's up to this I. Yes? So if your I is 2, you have computed only x sub 3 if it's a 3x3 system. But if I is 1, you have already computed x sub 2 and x sub 3. So for I, this is from I plus 1 to n are the ones that you already computed. So this sum has that many members here. So there's a little for loop summing this up. Remember those sums that they practiced supposedly?
Well, why would we write n minus 1 then? Wouldn't it just be n to 1?
Well, n I already did. But it would work if I type in n.
Oh, yeah, that's true.
But n is already done.
So if we're doing B3, would we do BI plus
So
1?
here you would just say A of I plus 1, yes, instead of B, because B we didn't change.
So basically, this is A of I plus 1, based on this here. I have 2 minus a mysterious sum and divided by what? A of I. So now we need mysterious sum. And this is, I suggest you write things like this.
Okay, this is a partially solved problem. Now I just have to figure this out. but it helps me to write things down. So write yourself a placeholder, okay?
Prior to the I plus 1, would you need like B of I minus?
Yes, and my B of I is actually that AI of I plus 1 in augmented matrix.
Oh.
This was written with B's because, well, last time I gave you an option to work with either augmented matrix or B's. I normally work with B, and I changed it up on the spot because I like mixing things up like that. So I'm amused. I have multiple endings. So there is a sum, and I know that I'm going to call them J's, go from I plus 1 to N, A of J times X of J. And this, based on exam 1, everybody now knows how to write the loop for, right? Right, I got a lot of smiles, like, right. Keep believing, Dr. Pradanovic, keep believing. Have faith. But does everybody agree with me that that's what the sum is? This one over here? I is 1, 1, 1. So this is my I. And these things grow from I plus 1 all the way to however many I have, which is N. It's my J. So you have to recognize a pattern. Right? This sum here. Yes.
I still don't get it. So we have x3, x2, x1. Don't we have to go in order from x3 to x1?
Yes, if it's a 3 by 3 problem. I want your program to work for 3 by 3 by 3 is what your example on the paper is.
Yeah.
That you're trying to generalize. What
We
if
want for bigger matrices.
3 by 3 you know how to solve by hand. You don't need a computer help.
Is your I going like down?
Yeah.
So your N is 3 right now.
So let's say that I is equal to 2. So 3 I have already. That's my last one, right? Let's say that I is equal to 2. That's N minus 1. This sum is X of 2. This is my B, really. This is A of 2, 3, right? Minus, and my mysterious sum is now just one of them, right?
How is that your B though?
That's where I stored it in an augmented matrix. It's the last column of the augmented matrix. This is actually, no, this is actually N. Ha, good catch.
N plus 1. Always the last column.
In my augmented matrix, it's that last one I tagged along.
Why is the formula So I have n-1 again.
Because x of n we already have. That's my bottom one
Okay,
that I kind of have.
okay, thank you.
It could start from n, it would actually kind of still work.
Okay, thank you.
It's just that your mysterious sum would be 0 and you would just divide things. Is everybody clear? This procedure I walked through and everybody was doing this and I took that as understanding, which is not necessarily the case. There might have been a miscommunication.
Wait, you have I on the n plus 1, then your n would be 2 bigger than your I.
If it's n plus 1 doesn't change in loop. It's always n plus 1. So it's always that last column in A that I add. Right? So it's 4. In this particular, the 3 by 3 case, it's always 4. So it's my 4th column, which is where my A was 3 by 3, and then I added a 4th column, correct? So that's where my B is. And the reason I don't want to use B is that I didn't change B in my forward elimination. I stored it in A, so I changed it all at the same time. So even if you just know this, do you agree with this? Can everybody write a program that computes this? I start with 0. And I don't want to type mysterious sum all the time. I'm just going to call it m sum, sorry. Shorter writing. Okay? So then I have for j is I plus 1 to n. M sum is m sum plus what? I'm listening, but I'm not hearing anything. My hearing is bad. It's not that bad.
Does it matter if you have the m sum initialized inside the second loop or not?
It has to be initialized always all over again to compute a new sum. At every stage, it's a new sum. So it matters, yes. So if you initialize it outside, -1 or -2 points, depending how I feel that day. Now let's see if I did this correctly or if I have problems in there. I have problems in there. Oh, yeah. So now let's see, what problems do I have? This is 5. Ah! My loop did not execute at all because I didn't put -1. Look at something. Control S. So if I save this as is, as I did, okay? Dr. Pradanovic -5 points on exam. My x stayed as 0, 0, so I didn't do anything there. And I didn't do anything because this loop has to have step -1 because it's descending. Otherwise, it's just not going to execute. If I have 2 here, 2 to 1 is an empty array.
you can see that if I type in 2 to 1, it's empty. 2 minus 1, 1 is actually an array 2, 1. Okay. All right, let's execute now. Control S. Haha. Mm-hmm.
Again, I did the same thing with Ren's code. Instead of having sum as a variable, I kind of just put it into.
You have to have a for loop for it, so it's not gonna work by putting in here. Okay? Because it's changing every time. You can't just type in everybody. How many elements you have in the sum depends on how big your system is and at which stage you are.
So every time you have a component that's changing.
You have to have a for loop. So you can't type things in directly. You can type things directly only when you know, oh, I have 4 elements that I'm adding up. If that 4 becomes 5, for loop. Yes? Now, how do I check that this is actually correct? What is A times X? What is my B? A times X minus B, if you will, should be 0. Yes? So whatever you get at the end, your A times X should be B, or else you didn't find X correctly.
That's great. Why do you run data from I plus 1 to I plus 1 to 1?
Because I started at the back, so my 1 is not computed, X of 1 is nothing. What you're thinking is forward elimination, not backward. You start from the end, so you have X of n computed, right? You don't have X of 1 computed, right? This sum here incorporates all of the X's that were already computed, and they're the ones in the back, they're not the ones in the front. So if I'm here X of 2, it's X of 3. It does not go down to 1. I don't have X of 1 yet. Right? So an X of 1 uses X of 2 and X of 3. Yes? Great. Now let's do something with this. So one problem that you actually have here in this code is that you're not doing partial pivoting. So if you encounter, this is problem number 1, if you encounter a 0 right here, if your A of JJ is 0, Houston, we have a problem. Okay? So you would have to actually switch rows to fix this. Right now, I'm not going to do this in class. Okay? What I will do, though, I will say if A of JJ is different from 0, do this, else display warning A of JJ is 0. Go fishing. It's going to be a joke for the rest of the semester. Something's fishing. Okay. So for now, I'll just display a warning. I'll deal with it later if I get there. So technically, I would have to exchange rows here and flip them over. I'm not going to do that right now. That might be your homework.
So I want you now to actually explore a little. Okay. Let's now create, yes. Here. So basically I'm just making sure I'm not dividing by 0. And if I encounter 0, I'm essentially just issuing a warning for now. That's all. Let's actually now use this. And you can technically either use your program that you just created or MATLAB operator. And let's see how long it takes to solve systems of size 1,000, 2,000, and 5,000. And some of you might not complete 5,000 by the end of the class. And I want you to find, so there's, if I do help on TikTok, okay. So if I do help on CPU time, it's a returns time in seconds. So I'm going to now create a test script. So I'm going to say my T0 is CPU time. And then I'm just going to solve, I'm going to create a large system. How do I create a random matrix that is 1,000 by 1,000? Rand or randi? I'm just going to do rand now. It doesn't matter. Rand of 1,000. And my B that is 1,000 by 1 is rand of 1,001. If I wanted to scale this to something that is between 0 and 10, what would I do? Sure. Let's do that, just for kicks. Now I will either use this problem that I solved or the problem. Okay, so I'm solving it. Alternative is just to do MATLAB version. So what is my elapsed time? So my CPU time returns just the current CPU time. So basically I record the time, do something, and then find another, record the time again and find the difference to see how long it took in seconds to actually solve something. So this is what helps CPU time. So here's T0, CPU time. Then I create matrix, solve the problem. T1 is the time after all of this has been completed. So what is my elapsed time? So let's actually see how long this takes. I'm going to save it. And I hope I don't get warnings with the problems. If I do, I will switch to MATLAB solution for this. So I'm going to save as. Why can't I save as something? Huh? Excuse me while I'm fighting with my... Does anybody see my save as? Thank you. It's not, yeah, never mind. It's normally, I guess I moved it somehow, so I'm gonna test timing. Whoa.
You had a x equals at line 7.
Yes. Thank you. Uh-oh. Still working on it. Oh, the mistake I made is I printed something out. Elapsed time, 12 seconds. So your 3 by 3 or your 5 by 5 looks instantaneous. 1,000 by 1,000. I'm guessing also, let's push it up a little.
Mine says 0.04 seconds.
So you have a faster for 1,000 by 1,000? There we go. So I'm gonna actually do this. N is 1,000, okay? So if I replace this by N, then I have saved myself retyping, so I can just change things. Let's do, okay? If I run, yes.
Is the elapsed time supposed to change every time already? Elapsed time? Is it supposed to change every time already?
Yes. It's gonna change slightly because your computer might be busy with something else. And oh, you know what the problem is? 38 seconds. So I went from 12 to 38. Okay. Now, why is it printing everything? Remember this part where we were debugging and we left that A after forward elimination? Remove it. Okay. Now let's test MATLAB and how good their engineers are. We don't know whether they're solving things with Gaussian elimination. They have a method behind that they're using. But I'm just gonna instead, on the same problem that took 38 seconds, okay? I'm gonna now use slash operator, which is a built-in routine. Let's see how faster it is. Damn! Beat me. Okay. So obviously, again, we don't know which method they're using. That's proprietary, but they have a selection of methods and they kind of optimize the problem behind it. So what we're doing here is we're gaining understanding about how things work. But if MATLAB has paid engineers to do this, then they better be better than what we can come up with here. Okay? So test it for 2,000, test it for 5,000. Can you even solve it with your Gaussian elimination business? Give it a test. Maybe not now, maybe we have time to wait for it. Okay? Be curious a little, like how good you are. And I'd like you to do a test for a number of ends. Let's say 5 of them that are growing. And how far they're growing might depend on your computer. So I'm not going to set the limits. Okay? And then test your program versus MATLAB and plot the timing for me until next class. Okay? Just to see, okay, how would you compare, how would you evaluate? Again, there's something in this exercise you will be asked to evaluate in your work life. How well is something doing? So you can go to understand, you program your little routine. Of course, you're slower than whatever software you're using. But you'd like to test to see, is it something worth buying? Based on this timing, I would buy MATLAB. Okay, right now. That's the kind of your computer. So I like actually
let's do that. So everybody do that. Try to push it to 5,000 if you can. Let's test different computers we have around the class. And some will be faster than the others. It depends on the processor. It depends on how much memory you have. Okay? So and I'll actually do a little report online just to gather that data. This is just the fun time. All right.
We submit the code for the script that we submitted today.
Actually, what I'll ask you is to just use it and report the timings. Just so that we have data we can all look at in class.